How old is the universe? We'll be going after that today, along with a couple other questions about the universe as a whole and cosmology. So congratulations, you've stumbled onto Extraordinary Concepts in Physics. I'm your lecturer who got the wrong size there. Teaching this course, also called Physics X, at Michigan Technological University. And if you just stumbled, welcome. Keep watching these lectures and other lectures. Hopefully we will scratch your cosmological itches today and with other lectures. First we'll go to something that we've discussed in other lectures, Hubble's constant. So Hubble's constant determines how fast the universe expands. And that's key because we know from listening to other lectures and believing me that the universe is expanding. And so one way to estimate the age of the universe is to just run that expansion movie backwards. And then everything comes together, every place. And you can determine the age of the universe from that, although it's not that accurate, it turns out, because it's hard to do. But let's go to the next. The graph where distance is plotted against velocity gives a line that tells, if you see something how far away, it tells you how fast it's going and how fast the universe is expanding. And the constant that multiplies the two is called Hubble's constant. And here we see three possible values, 50, 67, and 7, and 100. Let's go back. So today, it's been one of the major pushes in modern astronomy to come up with Hubble's constant. And it's pretty well determined now, although there's always a push for higher accuracy. There was trouble for a long time because galaxies near each other tend to cause each other to attract toward each other, and they move outside of what's called the Hubble flow, outside the clean expansion with the universe. So to a first approximation, everything expands with the universe, and the further away you are, the faster you go away from, from any place which is the center of the universe. However, galaxies near each other, they tend to want to attract each other and go in orbit around each other, and they develop velocities that are not part of the Hubble expansion. And those are called peculiar velocities. So it's been tough to get rid of the errors inherent in peculiar velocities in determining Hubble's constant. But through increasingly better telescopes, increasingly greater data and data analysis techniques, we've now determined that the expansion rate is 71 plus or minus 5 kilometers per second per megaparsec. So if something is 1 megaparsec away, it would be traveling on the average of 71 kilometers per second away from us. That's how that works. So here's a little quiz. Quiz your neighbors. So if the velocity is 7,100 kilometers per second, then what's its distance? It turns out that when you look out with a telescope, you can measure redshift, which tells you velocity relatively easily, something akin to velocity very easily. And then you're curious as how far away it is. And so when you're close by, there's many kinds of cosmological distance measures. But when you're close by, they all become pretty much the same, and you can say 100 megaparsecs. So a parsec, m means a million. Parsec is a unit of distance, and a parsec, I think, is 3.2 light years, or 3.2 light years per parsec, just so you know. You've seen that. So we're constantly interested to know, and it helps in determining the age of the universe, how far away things are. So the Hubble's constant game works for a while, but it doesn't work inside our solar system because there are no galaxies inside our solar system. Well, there's part of one, but it's too small a part of one to really be useful. So we have what's called the cosmological distance ladder, where each rung on the ladder tells us how to get further out in space. So for instance, we can determine the distance to the sun any number of ways. One good way is actually you can bounce radar off the sun. So you can give a radar pulse and you can bounce it bounces off the sun, comes back, you can time how long it takes, and you can see how long that is. And then you've gotten essentially one of the lowest rungs on the cosmological distance ladder. You cannot do this for distant galaxies. Distant galaxies are millions of light years away. So if you were to send out a radar pulse, you would have to wait millions of years for it to come back. And people are impatient. They don't want to wait the millions of years. They don't even want to wait the tens of years it would take to do the parallax to the nearest stars. to the distance of the nearest stars. So how that works is something completely different from determining the distance to the sun. It's parallax over the Earth. So what you do is you have the Earth goes around the sun. So here's the sun, international symbol of the sun. Here's the Earth. Earth goes around the sun, and there are distant stars out here. And as the Earth goes around the sun, the stars, with respect to distant stars, tend to shift with respect to each other. It's sort of like when you're driving with your car, the telephone poles have an angular speed higher than things out in the distance, than the moon out in the distance. So judging by how fast things go by, like telephone poles go by, you can estimate how far away those telephone poles are. So that gets us to the nearest stars. Star clusters, there's a different way. And then out to galaxies, the nearest galaxies, you have to look at a certain kind of variable star called a Cepheid variable star, which varies in a very precise way. And the longer it takes to vary, the intrinsically brighter it is. But even though if it appears to be dim, yet its period is very long, it might be supposed to be very bright, then it's strange. Then it has to be far away in order to appear so dim. So Cepheid variables give us another rung on the distance ladder. You see a picture of a Cepheid variable changing. Here it's not very bright. Here it's a little bit brighter. Here it's yet brighter again. And this is in the outskirts of one of the galaxies used to calibrate Hubble's constant, which is M100, a spiral galaxy that's not so far away. So Cepheid variables work for the nearest galaxies, supernovae. Then we see places where there are both Cepheid variables and supernovas. And then we can calibrate how bright supernovas are. And some supernovas is thought to be of relatively the same brightness. And then we can calibrate redshifts out into the distant universe. And that tells us how far away things are. So this shows you a star cluster. Well, actually you can't see it varying. Some of these stars actually change their brightness. And if you go to the Astronomy Picture of the Day APOD of October 12, 2004, among others, you will see a video where you'll see these stars change their brightness in a time-lapse sequence. And as they do, you can tell, because these stars change their brightness, you can tell how intrinsically bright they are. You can note just by looking at them how apparently bright they are. And once you have intrinsic brightness and apparent brightness, the only way you can get those two is to move things away and make something like the sun that's intrinsically bright apparently dim by moving it far away. And by knowing how far away you've moved it, well, you can get a certain brightness. Okay, so here's another one. This is the same galaxy taken with two pictures. So this is a Where's Waldo kind of question. If you can look at these, please try to find out which star here has gone supernovae. And so you can freeze it and invite your friends in, and you can then come to the conclusion that it's this star here that doesn't really appear very bright there. So part of modern astronomy is trying to find differences between galaxies so that you can determine distances to them. This one was easy. This one's real bright. It's the brightest thing there. This one faded already. For the age of the universe, you have to know several things. The age of the universe has to be older than the Earth. And we can date the Earth with other techniques, for instance, carbon dating. Things decay. Past that, we can estimate the ages of white dwarfs. And from that, we can estimate the ages from how hot they are. And you can get the universe, well, from the age of the Earth, you can say the universe has to be at least 3.5 billion years old. From white dwarf cooling, we can get the age of the universe has to be at least 12.5 billion years old. Globular clusters tend to indicate they're older. They're big clusters of stars that, let's see, these are white dwarfs. Here's a globular cluster. This is called the main sequence. Now stars evolve. The high mass stars are here and they evolve off the main sequence and they go over there. So if you have a whole cluster of stars, if you can find the turnoff mass here, that tells you how old the cluster is. If it's a really young cluster, then you'll just have all the stars in the main sequence here and none of them have moved off. If it's a really old cluster, you'll have none of the stars in the main sequence. You see a cluster of stars where none of them line up on the main sequence. That doesn't happen. We don't know a cluster that old. But if you have one that there's a turnoff mass, you can estimate its age by where the turnoff mass is. Okay, the most recent way is by calculating the spot size in the microwave background, and that combined with other methods tells us that right now we actually have a quite accurate age of the universe. We just determined in the past past few years to be much more accurately than ever known before. It turns out our universe today is 13.7 plus or minus 0.1 billion years old, and that is consistent with all the other measurements. So based on the microwave background, which looks like this, from analyzing the spots on the microwave background, the spot distribution, you get an age, and this age is 13.7 billion years old. Older than the Earth, older than the Sun. Very interesting. Helps us understand the universe. So with that, I will see you next time. We will discuss the Big Bang. See you then. Bye.